Welcome to today's class. It's environmental physics. And today we are going to learn about the different forms of renewable energy. In our previous discussions, we had looked at geothermal energy. We had looked at biomass. We had looked at the other forms of non-renewable forms of energy. So today we're just going to go straight into nuclear energy. And nuclear energy basically comes from nuclear fission and the nuclear fusion. Nuclear fusion is basically the breaking of a heavy nuclei into two or more smaller lighter nuclei, and in the process there is emission of energy. Nuclear fission, on the other hand, it is the combining of two lighter nuclei to form a heavy nucleus. Let's look at nuclear fission. As you can see on the diagram, there is a large nuclei, which is uranium-235, which is absorbing a neutron. And in the process, it's breaking down into Kr and Ba, which have smaller masses than the original. And in the process, they are releasing some 3 neutrons here. This one represents what we call uncontrolled nuclear fission, whereby these 3 neutrons can go ahead to be able to bombard other uranium atoms and also be able to produce more. So like if we begin with 3 neutrons, we'll end up with the like 6, going to 9, 18. So after a while, it will be an uncontrolled nuclear fission because there are more and more neutrons which are being produced, and each one of them can be able to break down a larger fuel rod. On the right-hand side, you can be able to see a controlled nuclear fission. A controlled nuclear fission is where all the neutrons which are produced are absorbed except one, so that one can be able to continue colliding with other fuel cells, all fuel rods. So in the process, you get that there are not very many neutrons which are being produced. The rest of them, they can be absorbed using what you call a moderator. And the moderator can actually be something like water or graphite rods. So in a controlled chain reaction, a heavy nucleus is bombarded with a neutron. It is split, but one neutron, all but one neutron is absorbed. This one is now what is produced in a nuclear reactor or in a nuclear generator where nuclear energy is produced. And you can be able to see in this example here, the neutron comes in, it gets absorbed. A neutron is neutral, so it can be able to easily it can easily be able to be directed towards the nucleus. And once it has been absorbed, it makes the neutron to be very, very unstable. And so in the process, it can be able to break down, producing either 3 neutrons or 2 neutrons for the case of this second nuclear reaction. So the process depends on the presence of a moderator. Moderator is what is going to absorb the neutrons. It can be water or graphite, and it is, or we also call it a coolant. So the reactor core, or what you're calling now the fuel rods, that's uranium rods, it is housed in a steel pressure vessel so that water can be able to move around it, especially for controlling of temperature. So if you can be able to look at the diagram here, you can see we have a containment building where we have our primary fuel cells. You have the uranium fuels, and of course now a neutron is going to be introduced inside here, and that neutron will be able to initiate the chain reaction. And inside here now we also have liquid water under very high pressure, which is going to carry the heat to the steam generator. So once the heat has been produced, then there's a heat exchanger here, whereby steam, which is water, which is being able to flow, can be heated. It turns into steam. The steam now can be able to move a turbine. And as the turbine is moved, you know that from physics point of view, wherever there is movement of either the magnet or the coils, then an EMF is going to be induced. That is going to be stepped up and taken to the grid system. So once that steam has actually been passed, it will be, there's a system where it is going to be taken back, it is condensed, and then it can be recycled inside the nuclear reactor. So what are the advantages of nuclear power plants? The energy is released is extremely large, so it can bring down the cost of electricity, and the amount of initial fuel required is very small. The main disadvantages is that the products are used and the byproducts generate what we call they produce radioactive waste. They produce the radioactive substances, the gamma rays and all the beta particles, and this can be harmful to man. And also the installation cost is very, very high to start. That is why most developing countries have not yet had one. Then there's a concept which we call the nuclear meltdown. This one may take place especially if the coolant fails to work, such that there's a very high temperature which can be able to take place. So if that one happens, then it can be able to cause damage due to the high heat which is produced. Typically, this stems from the loss of the coolant. This can and so the coolant circulation through the reactor causes loss, or it stops altogether, and therefore the temperature goes very high. So it can lead to what you call the nuclear reactor undergoing a meltdown. Of course, this now can be dangerous. Then you also have what you call radioactive waste. As we have said, once the fuel has been used, it becomes spent fuel. So where does this spent fuel go? It needs to be disposed of. So we have listed here some of the ways in which it can be disposed. It can be undergo what you call deep geological burial. It can be buried deep in the underground, or above the ground. They can create what you call mausoleums at the Arctic ice there, all beneath the ocean floor. Underwater storage is also possible. And also we have what you call concrete and the steel cask. The steel cask is shown on the next diagram here, where the spent fuel is hidden right in deep in there, and then surrounding it is what you call a canister of steel. So from your physics, you know that the strongest rays, especially the gamma rays, they cannot be able to penetrate steel or concrete, so they can be able to be contained, and therefore this way it can be disposed of safely, and it cannot be able to leak and cause harm to the environment. On the right-hand side, you can also be able to see some underground kind of storage, where all these things are actually storing all those spent fuel. We have a worked example here where you can be able to calculate the energy. And I think the key thing here is being able to use this formula here. We have learned this formula here. Energy, that is the Einstein equation, is equals to M, which is the mass. Actually, it is delta M, which is the change in mass, and then multiplied by the square of the speed of light. So our task here is basically to look for the change in mass, because when you look at this equation here, there are some dots here. Like for example, 238, it is 238.050784 atomic mass units. So if you can be able to get the mass of on the left-hand side and the right-hand side, then the difference is actually what we call the delta M. And as you can be able to see here, if we total up 140, which is exactly 139.92161, and then 3 times of the neutrons, we have the mass of a neutron. When you total that one and then you subtract from 238 point that, then our delta M is equals to 0.1837991 atomic mass units, which you can convert to kilograms. And then using this formula here, you can be able to get that our answer is 171.2 mega electron volts. So that is just a calculation how you can be able to get the amount of energy which is being produced. And you can see it is quite a lot of energy which is being produced here. And it's given in electron volts, and it is in a mega electron volt. And then another point just to note here is that usually nuclear reactor, we use either uranium-235 or uranium, or this is plutonium. It is because that the nuclear force is more attractive for an even number of neutrons in the nucleus than for an odd number. So when you try to subtract, for example, for this uranium here, you'll be able to get that. If you are able to subtract, you'll get, for example, uranium-235. It has an atomic number of somewhere here. It's an atomic number of 92. So if we try to subtract, I have my calculator here. If we try to subtract our 235, you subtract 92, you get 143. So this 143, it means those are the number of neutrons which will actually be present in this atomic in this nucleus. So the statement which you've made here is that when you are having what you call the neutron approaching 235, it gets an odd number of neutrons, and therefore the force there becomes attractive, so that they can be able to have an even number of neutrons, which now can be able to increase the stability of that nucleus. So you get that 235 and 239, they will be able to produce an odd number of neutrons, and therefore it makes it possible for a neutron to be able to approach and therefore be absorbed for the nuclear reaction to take place. I think that is it as far as the nuclear reaction or nuclear energy is concerned. But maybe we also need to remind ourselves something about the nuclear fusion. Nuclear fusion usually takes place when lighter nuclei, especially we have the isotopes of hydrogen. One of them is deuterium and the tritium. So when these ones combine, they can be able to form a heavier nucleus. But this one has not been practically possible because of the high temperatures which are required to be able to make the lighter nuclei to be able to fuse. So currently, in the nuclear reactors which you have, they are making use of nuclear fission. So we also talk about hydroelectric energy. Hydroelectric energy is a renewable source of energy, and it needs these four main components to be able to produce hydroelectric energy. We need a dam, which will be able to hold the water. We call it actually the reservoir, where now the water is going to be contained. And then we need a turbine, which is going to convert our kinetic energy into electrical energy. You also need a generator, which will now be able to convert that mechanical energy into electrical energy. And then you need some transmission lines to be able to take that energy that's been produced into a grid system. So once you have those ones, then there are two main factors which determine the hydroelectric power. One of them is the water flow, what you're calling the flow rate. That means the amount of water which is able to flow to the turbines. And then you have what you call the hydraulic head height. This is actually the difference between where the water dam is, the reservoir, and also where our turbines are located. So that difference in height should be large enough to ensure that there's enough mechanical energy to be able to produce a feasible amount of electrical energy. So hydroelectric power will be given by gravity multiplied by the water flow rate multiplied by the head height. So you need to understand those terminologies. What are the positive impacts of hydroelectric power? It's a clean source of energy. It does not emit any what you call the greenhouse gases. It's not radioactive, and they do not require any any kind of combustion risk. So it is a very clean source of energy, and I believe this is what we are mainly using even in our country here. What are some of the negative impacts of electric power? The turbines usually generate a lot of noise, and so that noise pollution can be a damage to the surrounding ecosystems. The water near the surface of the dam can become warmer, which will lower the oxygen content of the water and negatively impact certain species of plants and animals in the environment. And then number 3, the height of the water level may be frequently, the height may change. Therefore, those plants, especially which are at the shoreline, may not be able to get enough water levels. And also the dams may make it difficult for fish to migrate up or downstream. And so this can also maybe impede the movement of the fish. I just, especially now for the transmission of electrical energy, we just need to remind ourselves of the transformer equations, where we have the, where now this one represents the electrical signal which comes in, it is an AC kind of current or voltage, which now needs to be stepped up or down. Remember that you need to step up the electrical energy for purposes of minimizing what you call the power losses. I believe you can be able to recall that during transmission. So these are some of the formulas which are used. The number of turns in the primary coil divided by the number of turns in the secondary coil is equals to the voltage in the primary divided by the voltage in the secondary. Or for current, now that one will be inversely proportional there. And then we call it the turns ratio, and also the power, which is voltage times current. For an ideal transformer, the power transmission is actually consistent. It's the same. If the efficiency of the transformer is 100%, then all the power in the primary transformer will be transferred to the secondary coil. We have an example here, which you can be able to look at. And the first question is asking, what is a national grid? You know that a grid is an interconnection of different power generators. May they be wind, solar, electrical. So once they are connected into a common grid for the purposes of being transferred to the rest of the country, then we call that a national grid. Then you're also asked to calculate the current in the secondary coil and the power loss during transmission. So that example has been done for us. Yes, it has been. It has not been done for us, but I'm sure you can be able to use these equations which we have. What is the current? We can be able to use these equations which I've shown on this side here, and we can be able to calculate the power. So the current you can be able to use, for instance, this equation here. So if we have our power in the primary coil, we can just be able to look at that one. So if we have we have what we call the current in the secondary coil. So you can be able to use our V1, or in the primary, current in the primary is equals to voltage in the secondary, current in the secondary coil. You can see the voltage in the primary coil, it is 160 kV, multiplied by the current in the primary coil. Not really. The voltage in the primary coil is actually 11 kV, kilovolts. The current in the primary coil is 1. The voltage in the secondary is 160. So you clearly see you can be able to get the current by dividing 11 kV over 160, which if you use your calc, you should be able to get something like 11 divided by 160. So it should give you something like 0.06875 amperes. And then you can also be able to calculate the power loss. Remember, the power loss is calculated using I squared R. So the power you have gotten here is 0.068 multiplied by the resistance. If you can be able to see, you can see the resistance is 10. So I squared R, you can be able to get the answer. And then there's also another question there about an AC circuit. You're supposed to determine the voltage and the current through the circuit elements. This one has also been done. Just one thing I need to remind you is that, you know, for AC, the way you can create maybe we have what you call reactance. Reactance is the resistance. It is the total resistance we get in an AC, in an AC circuit. For instance, if it's a capacitor, the reactance there is given by 1 over omega C, where omega is the angular frequency given by 2 pi f. And so you can be able to see that one has been calculated for you. So the kind of resistance you get here, we are calling it capacitive reactance, because it is just obtained as the AC is flowing through the capacitor. And also we have what you call the inductive reactance. Inductive reactance is actually when the AC is flowing through an inductor coil, then there's also a resistance associated with it, which is given by omega L, where L is the inductance of that particular coil. And so this one has also been done for you, and I'm sure you can be able to follow it up. Good. So from from that, then we can be able to move on. But I'm sure if you have a question, even as you move along, don't hesitate to ask a question, so that we can be able to move together along. Then you go to nuclear fusion. I think this one was we have talked about earlier on, that deuterium and tritium can be able to combine together to give you a heavier nuclide, which is helium, and in the process, a lot of energy can be produced. Let us go to wind energy. Let's go to wind energy. And in wind energy, we find it in areas which are very windy. In Kenya here, we have, for example, the Ngong Hills there, and some areas of Turkana there. Places where there's a lot of wind, then windmills can be erected. A windmill consists of a fan-like structure erected on a strong standing support at a considerable height. The strong wind moves the wings of the windmill, and this turns the turbine of the electric generator. So basically, we also have mechanical energy being converted to electrical energy. So a single windmill produces very small amount of electrical energy. So we have several of them. We have what you call a wind energy farm, which has several windmills, and so the output can be connected together to give a larger electrical output. There's some technology. There have been some technological developments as far as wind energy is concerned. We are having turbines which are a bit larger, so they can be able to produce more kilowatts of energy. Then we have wind turbines which are more controllable and grid compatible. So here we are talking about they are incorporated with what we call AC to DC converters and modern electronic components, which can be able to enable the designers to control the output. So this way, then the energy which you get from there, it is more convertible to the grid. Remember, we talked about what is a national grid, and so even the wind energy can be incorporated in there because of the inclusion of some electric conversion systems, which now can be able to ensure that there's some consistency in the output of the wind energy. And also we have wind turbines which have fewer components, and this one can also be able to improve what you call the reliability and even lower the cost of installing the wind turbines. So basically, what is a wind turbine? Down here, you can be able to see a wind turbine in this slide. And as you can be able to see, figure number 1 shows some wind, which is blowing from left towards the right. And then number 3 here shows the blades of our wind turbine, which are going to rotate. And then as they rotate, now we can be able to come up with what you call number 4. You can be able to see the main turbine shaft, which connects the spinning blades to the inner workings of the machine. So then we can be able to go to it as what you call a brake, number 5. And the function of the brake, you can see it is to prevent the mechanical failure from high wind. Sometimes the wind can be very, very high. So the brakes are put in there that when the speed exceeds a particular limit, it can be able to disconnect it from the turbine to prevent what you call mechanical failure. And then we have what you call, from there now, the key thing again is the wind generator number 8 here. We have already know the inner workings of a generator, how it's able to convert now the mechanical energy into the electrical energy. And then you can be able to see number 10 there, or number 14, the turbine tower, which contains the wiring so that the generator can send electrical energy into a transformer. So number 14, I'm able to see it there. Now from this point, it is where now we are taking the mechanical energy to our transformer for onward electrical transmission. What are the advantages of wind energy? It's environmentally friendly, it is renewable, and only the construction expense is involved, but the maintenance, it is much, much less. What are the disadvantages? The initial establishment is very high. It cannot be established everywhere because of the requirement of open space, and also the winds are blowing at a speed which is greater than 15 kilometers per hour. So we really have to do some feasibility studies to ensure that it is erected in the right place. Good. My last presentation will be on ocean energy. And in ocean energy, a lot of, you can be able to get a lot of renewable energy from the ocean. And this comes in the form of tidal streams, ocean currents, what you call a tidal range, and ocean waves, and what you call the ocean thermal energy. So let's just look at maybe 2 of them. First of all is the wind energy. Here you have wind. We have a turbine somewhere here, and then there's a piston here. So you know the waves, the waves, they go in a rhythmic manner. There is rising and falling. So this structure is constructed in such a way that during the rise and during the fall, the piston can still be able to move and it can be able to rotate a turbine. So when it is rising, when a wave is rising, it's able to push the piston, and the piston can be able to rotate an attached turbine here. When it falls, it creates what we call a low, it creates something like a vacuum inside here. And that vacuum which has been created, now the atmospheric pressure can be able to push the piston downwards. And in that movement also, we still have the piston as it's moving up or down, it is still able to rotate a particular turbine. So I've been able to explain that. So the piston is connected to a turbine which rotates the electricity, which rotates the turbine, and it can be able to produce electricity. So you can see the advantages and the disadvantages. And let me also talk about the ocean thermal energy. So this one makes use of the fact that there's a difference in temperature between the different layers of the ocean, and that one can, especially if you have a volatile liquid like ammonia, it can be used to produce electricity. How does that happen? As you can see here, there's a turbine, and there is, no, this is rather the sun. Yes. So water at the surface, it's at a higher temperature, especially when it is heated during the daytime. And then the water at the bottom is at a lower temperature. So the water which is at the surface, as it heats up, then it is connected to a liquid, which like ammonia. Ammonia has a property that it's very volatile. So as it vaporizes, as it changes into vapor, you can be able to pass through a turbine, which now can be able to move the generator, and the electricity is produced. Once it goes through the turbine, then it is condensed. It is condensed by the cold water at the bottom. So once it is condensed, then it can again start the service. It's condensed, it comes in contact with the warm water, it's vaporized again. So this liquid ammonia keeps on circulating, and in the process, can be able to run our turbine, which can be able to generate electricity. So I think I've been able to explain that. That is the work which has been explained. The advantages and the disadvantages are shown there. And that actually marks the end of that kind of presentation. So I'm going to just invite maybe if there is any clarification or any question which needs to be done, and